Hello. In our last lecture, we have discussed about how the TLS protocol works. There we have two levels in TLS protocol, which is one is TLS handshake protocol, which is responsible for uh, uh, agreeing upon the cipher suit and exchanging the key. And next, we have the TLS record protocol, which is responsible for data transmission. So now let's look at some more information about TLS record layer operations. There, the the purpose of TLS record layer is to encrypt the application data for the transmission. So when we have the application data coming from the application layer, first they are fragmented. Fragmented means they are divided into equal size portions to make packets, and then this each fragment is compressed to reduce the redundancies. So that is compression is an important feature in data transmission, because we can save a huge amount of bandwidth when we have proper compression on data. Huge save the bandwidth and make the transmission efficient, uh, likewise. And once we do the compression, we have a relatively smaller size than the original data fragment. And then upon the compressed portion, we execute the hashing. We do the hashing, and hashed MAC is there. That is one reason to provide kind of authentication, authenticate the sender to the receiver, and also we can give some kind of integrity when we have a hash message authentication code, hash MAC. And also for the hashing, we have a key value and also a sequence number. The sequence number is responsible to indicate that all the fragmented sequence are clearly received to the receiver. So receiver can check all the sequences are clearly received using that sequence number. So the salt values for the hash MAC is the compressed data fragment, sequence number, and also the key for the message authentication code operation. And once we have that hash tag, message authentication code tag, we we add that part with the compressed data portion, and also for the rest of the things to make the packet somewhat equal size, we add some kind of a padding. Like if we use block ciphers, we have to have the block in equal sizes. So therefore we have to have some kind of padding to make the blocks are in the same size. So we create that data portion as a first we fragment the data fragment is first the application data is fragmented, and each fragment is compressed, and on this compressed data portion we do the message authentication code operation, and also we do some kind of a padding, and together as a concatenated value of these two compressed data portion and MAC and padded value, we create a block of data for the encryption. So that is when we use block ciphers for encryption, and we do the block cipher operation and do the encryption, and we add a header value for that encrypted block, and this block is now ready for the next layer, that is transport layer. So it is sent to the transport layer. So application data is processed like this and then sent to the transport layer. So this is how the record layer operations are happening in the TLS protocol. Here is a kind of a, in this slide shows us kind of a summary about this TLS entire protocol, the handshake and the record layer. In the handshake layer, we do the agreement on the cipher suite to be used, and then exchange the session key for the data transmission for encryption. And once the session key is and also before establishing the session key, the authentication is done, and then the session key is transmitted between the parties, and then that session key is used for data encryption in the record layer. This slide shows just the summary of what we have discussed so far. And there are when we have this TLS protocol, we have some security considerations in this TLS protocol. So we have to have this trust and digital certificates in our setup, because in the TLS handshake protocol, usually the server authenticates to the client. So that is done using the digital certificate. So TLS uses public keys provided in digital certificates. So because of the digital certificate, the public key is going to be trusted by the client. And how these digital certificates are achieved is we discussed in our previous lecture. So there is a trusted certification authorities, and because of that trust, clients will use the server's certificate. So certificate should be verified, require tracing certificate pathways, like the server certificate should be shown to the client, and client will look at the root certificate which has signed the server certificate. Because client trusts the root certificate, the public key in the root certificate, because of that trust, client is going to trust the server certificate. So web browsers come with pre-configured list of root certificates. So certification authority, they provide their root certificates to all the client browsers. So usually in client browsers and operating systems or the device hardware, these kind of things, the root certificates or the root certificates of the trusted certification authorities are pre-configured. So when we get our device, when we get our web browser, when we get our mobile phone or whatever device we connect to the internet, that root certificates are pre-configured at their production. So because of that trust, we trust that certification authority, we trust the root certificate, and anything signed by that root certificate's public sign-in key is going to be trusted by our devices. That's how this trust chain is built up. And when we talk about the authentication, this authentication is one-way authentication most of the time. Usually server authenticates himself to the client, but not the mutual authentication. Client is not going to authenticate himself to the server, but server always authenticates himself to the client, because most of the time the server doesn't want any authentication about the client. Client just send a request to get some data, and server is responsible for sending that data through a secure channel. Because of that, we have the handshake protocol, and in the handshake protocol, the server should authenticate himself to the client, because otherwise client is going to get the requested data not from the original server but some fake party. To prevent that, server authentication is there, that authentication part is there using that public key infrastructure, like showing the server's certificate. So typically authentication of users is not performed in handshake. typically, but that can be also done if it is needed. Password authentication or serve authentication is happened in the HTTP channel. It's like when we log into our Facebook account or email account, we have to authenticate ourselves by sending our password. From that point onward, the server identifies this is that particular user, and from that point onward, no client authentication is needed to data transmission in this session. But server needs to authenticate himself. So HTTP protocol or the HTTPS or the TLS protocol suite is typically not doing client authentication to the server, but instead we have to have some kind of a password-based authentication to log into that server, and from that point onward, once we have that secure session or the channel established using this TLS handshake protocol, we don't need the client to authenticate the server again. So typically the client authentication is not in this TLS handshake protocol. But I mentioned the importance of having server authentication there, because otherwise client might get something not from the original server but from a fake party. And when we talk about this TLS protocol suite, specifically the handshake protocol, we have to address some kind of forward secrecy. So usually it is called forward secrecy. We have the term perfect forward secrecy. Generally the idea about this forward secrecy is this is coming with the key exchange happening in this the handshake protocol. So we have several key exchange protocols. We have RSA based key exchange, or we have Diffie-Hellman based, the plain Diffie-Hellman, which is not authenticate to each other, but we have to have some kind of authentication in Diffie-Hellman key exchange. For that purpose, we have signed Diffie-Hellman or some kind, or likewise. So we have to have kind of a forward secrecy. What is the meaning of forward secrecy? An adversary who later learns the server's long-term private key shouldn't be able to read previous transmissions. So if you have followed our lectures about discrete logarithm ciphers, there we discussed about the Diffie-Hellman key exchange. We talked about long-term keys and femoral keys. So if an attacker gets a party's long-term key, long-term secret key, if there is no freshness in this key exchange, that freshness, that means not using femoral keys, if there's nothing like that, the attacker can get all the future messages, because attacker knows that long-term keys are the only thing you exchange by the two parties, and because of that attacker can derive the session key or the key between those two parties, and since there is no freshness added for each new session, this entire that secret key is going to be fixed between those two parties. So once it is get at some point, all the future encrypted communications can be decrypted by the attacker, and also the past communication channels communication happen between two parties. But if there is a freshness, that means for each and every new session, even though we have long-term key pairs, long-term keys are used to authenticate each other, but for the purpose of adding some fresh security for each session, we have to have femoral keys. Femoral keys are keys particular for that session only, and for the next session that key is going to be changed, refreshed. So if we have that sort of setup, freshness is there, and even though attacker can get set of previous keys exchanged by the two parties, attacker will not be able to derive the future keys. So future communications are going to be secure. Attacker cannot decrypt them, but attacker may be able to get all the past communications, but not the future ones. So that idea is forward secrecy. So when we have RSA based key establishment, there is no perfect forward secrecy or forward secrecy, because RSA is just encryption of encryption using the is a public key encryption, and there is no use of freshness or ephemeral keys there. All the long-term keys are used for the encryption, and if somebody encrypts his value, his session key using a RSA encryption, that means if the RSA the secret key is revealed to the attacker, attacker can get the exchange value, and based on that, attacker can derive the key which is used for encryption in the record layer. So no perfect forward secrecy is addressed in RSA based key transportation. But when we have Diffie-Hellman type, plain Diffie-Hellman doesn't have perfect forward secrecy because they are based on just the long-term key pairs, private and public. But when we have signed Diffie-Hellman, and signed Diffie-Hellman means long-term keys are used from the sign-in process, but for the RSA computation, they use fresh keys for every session. Or sometimes we can have kind of RSA computation, but for that computation, for each and every session they use a fresh private key. And also RSA public RSA long-term, the Diffie-Hellman long-term key pairs are also there. So using both long-term and ephemeral keys, there's a possibility of deriving a session key. In that way, even without signed signed Diffie-Hellman, it is possible to get forward secrecy in kind of RSA Diffie-Hellman setup. So mostly, generally, RSA-based key exchange mechanisms do not provide the forward secrecy, but Diffie-Hellman based key exchange mechanisms have the potential to provide forward secrecy facilities. That's like generally. So in practice, if there are RSA key transport mechanism, there is no forward secrecy, but signed Diffie-Hellman provides perfect forward secrecy. So we have to consider these things when we design our public key infrastructure, the protocols to be used. And some statistics are there. These are not new, but all statistics. So forward secrecy is not supported about 29% for web servers. Another consideration is deprecated features, small RSA keys. We know that to get the maximum benefit of RSA signature scheme for authentication, we have to have the RSA that key length in certain size. So below 2048 bits, it is not going to be that secure. So researchers can break 768-bit RSA keys. So even though we use RSA, in theory it is secure based on that mathematical hardness, the computation hardness of this RSA problem. We cannot say RSA scheme is secure because researchers now can break 768-bit RSA keys. So likely that government agencies can break 1024-bit RSA keys most of the time. So servers should use at least 2048-bit RSA keys or 256-bit elliptic curve keys for if they use RSA scheme for authentication. Otherwise, below 2048 bits, we cannot get the expected feature about this scheme. So that's not a weakness of this RSA algorithm. It is weakness of using smaller keys. Smaller keys are vulnerable for attacks. And other thing is, other feature, deprecated feature is data compression. We know that data compression is important to save the bandwidth and also reduce the redundancy in plain text. That sort of benefits are there from the encryption compression, but data compression is also make some vulnerabilities for certain attacks. So crime attack is one such attack. I'm not going to talk details about this crime attack, and also there's another attack called breach attack. So the idea of these attacks are they get certain information about the plain text using some leaking information from this data compression. It's like attacker is trying to inject some part of data and compress that data together with uh, the secret value or the secret message that is going to be in the client or the server side. So in there, if the data is going to be highly compressed, attacker knows that most of the portion in the inject value is going to be overlapped with the secret message. If it is not going to be so much compressed, attacker can have some idea of the injected value is not going to be very much overlap with the secret value. So that sort of thinking pattern is there in this attack. You can read about this crime attack, breach attack, and also the theoretical background about compression-based leakage attack, which is proposed by John Kelsey, I think, a long time ago. I will give the links to those research papers if you are interested. So data compression is something we have to handle carefully. Even though it is a good feature, it provides some benefits as a saving bandwidth and reducing the redundancy. So as for data communication and for security, it is a good feature, but there are certain vulnerabilities coming because of the data compression. And also using RC4 cipher, which is a stream cipher. When we have this RC4 stream cipher, the key stream of this RC4 stream cipher, if you have followed the stream cipher lectures, you will know about this. What are the terms like key stream, plain text stream, and ciphertext stream? How the stream ciphers works. So generally, when we put a seed value to the stream cipher, it will generate a key stream. So key stream bits will be XORed with the plain text bits and generate the ciphertext stream. So in this setup, the key stream generated by the stream cipher should be pseudo-random, at least look random. But actually there are small biases that makes it look non-random when it comes to RC4 setup. So the researchers found that biases, and because of that now RC4 is not going to be a wise decision to be used as a stream cipher. So RC4 should be disabled, but for kind of stream cipher encryption we have to use another stream ciphers, not the RC4. RC4 is now kind of outdated. And SHA1 certificates. So SHA1 is secure hash algorithm 1, which is the first first algorithm in this SHA setup, SHA family. So digital signatures are only secure if the hash function is collision resistant. We have discussed about collision resistance and digital signatures in our digital signature lectures. So idea about this slide is, now this SHA-1 hash function is not collision resistant. Researchers, by the time I create these slides, researchers are getting very close to find collisions in SHA-1. So now it is recommended that SHA-1 hash function should not be used for sign-in purposes. So it is kind of outdated. So now new servers use SHA-256 or 512 like modern SHA algorithms, not SHA-1. So servers should stop using SHA-1 certificates by December 2015. So December 2015 SHA-1 is disabled in most of the servers. Now they use modern SHA algorithms for hashing. So these are the considerations when we use this TLS protocol suite to get this expected security. So we can definitely make our communication and channel secure, but we have to use the cipher suites or the ciphers for different purposes, like for stream cipher operations we should not use RC4 anymore. For signature schemes and for hashing we should not use SHA-1 anymore, even though the SHA algorithms and stream ciphers and RSA and everything provide security, but we have to carefully choose the algorithms to be used and also the key sizes according to the current attack possibilities. So these are some considerations we have to consider when using TLS protocol suite. Even though these algorithms are theoretically correct, depending on the current situations and the capabilities of the machines, the powers of the machines and the powers of the attackers, some of the things should be adjusted in certain ways. So mostly like outdated things should be eliminated. And TLS 1.3 version, it is considered the next generation, currently under development at the IETF, Internet Engineering Task Force. The primary goal is remove cipher suites without forward secrecy. We discussed about forward secrecy. In TLS 1.2, that's the old version of TLS, and there we have certain cipher suites which are without forward secrecy. So like RSA based key exchange. So once researchers identify these kind of attacks, these kind of features, in the next generation, the next version, it is recommended to remove those things from the protocol suite. So then nobody's nobody will accidentally use them when we use the protocol suite. And other goal is remove obsolete deprecated algorithms. It's like outdated ones, and provide low latency mode for fewer round trips. So that's like round trips means like client send a message to server, server send another message to client. That is one round, and the next round likewise to make the protocol more efficient. It is uh, needed to lower this number of round trips. So that is considered in this new TLS version to make the communication efficient, and encrypt more of the handshake to improve privacy. So this is deployed already. Uh, Even though we use TLS 1.2 in certain places, this is the latest one and the safest one. And also another thing is we have to consider about cross-site request forgery attacks, CSRF. So cross-site request forgery is also known as one-click attack or session riding. CSRF is an attack that forces the end user to execute unwanted actions on the web application in which they are currently authenticated. CSRF attacks specifically target state-changing requests, not theft of data. With a little help of social engineering, such as sending a link via email or chat, an attacker may trick the users of a web application into executing actions of the attacker's choosing. So this is like, let's say you are logged into your Facebook account and somebody sends a chat sending you a link. So now you are in your authenticate, like you authenticate yourself to your server and you are logged in there. Somebody sends a link, and by clicking that link you can directly communicate to the Facebook server from your account. So that can be a link, like somebody sends a link to a picture or something like a shopping site or something like that. But actually, the idea of this underlying algorithm running in that link is to maybe change your age or change your name, maybe to disable your Facebook account, something like some unwanted thing to you, but it is coming as a hidden request. So that is called cross-site request forgery. Somebody else is sending a link while you are logged into your legitimate account, and through clicking that link, you communicate to the server, your Facebook server, from your account to do a certain state change. So that is legally authenticated because it is coming from your account. Server will do that, but it is not something you expected. So that is the idea of cross-site request forgery attacks. You can read about these kind of things in internet to enhance your knowledge. And yeah, using TLS on a web server, we will going to discuss about this topic in our next lecture. For the time being, we have discussed about how this TLS record protocol works, what are the operations there, and when we use TLS protocol suite, what are the things we have to consider. So what are the vulnerabilities, potential vulnerabilities, what are the uh, possible attacks. So based on the theoretical attacks and attacks on the algorithms, certain algorithms are going to be outdated, and we have to use the latest ones to make our communication secure. So as a security engineers, security engineers, they do kind of a, once they implement a website or system, they do kind of a penetration testing. In there, they look at what are the algorithms running in the TLS protocol suite, and they identify the set of algorithms and features and the key sizes, that sort of things. So they analyze that, and once the guideline is set, these key sizes are vulnerable, these algorithms are vulnerable, what they have to do is they have to remove them and use the currently the latest technologies, latest what you call uh, recommendations in the web service. So that's the idea about the things we have discussed so far in this in today's lecture. So in our next lecture, we'll discuss about how to get this the TLS on web servers, how the certificates are obtained. Okay, thank you.